So the topic I'll be talking about this afternoon is sort of a bit of a refreshing change maybe to a lot of the big data talks, which have been very, very interesting. But this is more of the classic high-performance computing for modeling and simulation, which is a forte of the Flash Center. And what I'll be telling you about this afternoon is efforts at scientific discovery through HPC simulations of high-energy density physics experiments. And I'll explain to you right now what that means and what that is. So it's possible to think about phenomena in the universe, and in particular in astrophysics and cosmology, in terms of a plane that involves the density along this axis, with going to higher densities in this direction, and higher temperatures in the vertical direction. And if you plot phenomena on this plane, then you can see that there's different kinds of astrophysical phenomena or objects, the sun sitting right here. And it's turned out that by using very high-powered lasers and different experimental setups and targets, that's been possible to reach very high pressures, very high temperatures and densities, and therefore begin to learn things about these phenomena, these objects that heretofore were not possible to learn about in the laboratory or with computer simulations. And what's really made and driven this field is that there's a widespread availability now of facilities where experiments can be conducted in high-energy density physics. And among the facilities there's a wealth of smaller laser facilities at universities in this country and overseas. There's also experimental facilities at particular laboratories that universities and laboratory experimentalists and scientists access. For example, overseas include Lully in Paris, the Vulcan facility at the Rutherford Appleton Laboratory in the UK, and Felix in Darmstadt in Germany. In the US, among the premier facilities nationally are the Z-pinch machine, or the Z machine at Sandia National Laboratories in Albuquerque, the Omega Laser Facility at the University of Rochester, Laboratory for Laser Energetics, and the Titan and Jupiter lasers at Livermore. And finally, the largest facility in this country and in the world in terms of the kind of laser energies that are available to be directed towards experiments is the National Ignition Facility at Livermore National Lab. So those are the sort of experimental facilities, sort of, you might say, the hardware in some sense in this discovery enterprise. But what I want to emphasize and tell you a little bit about here today is the importance of software, of application code, but particularly the special importance of it in this particular area. In order for academic experimentalists to exploit these facilities, open codes are needed that can accurately simulate the experiments and do simulations. These HEDP experiments are difficult, they're expensive, it's infrequent access to these facilities, and often they're very sparse diagnostics. So simulations, as a consequence, have a vital role to play in the design of the experiments, because you want to make sure your experiment is, first of all, not going to damage the facility, but also has a chance of getting you the scientific results that you're looking for, answering the science questions that you want answers to. And they also has an extremely important role to play in the analysis and interpretation and understanding of experiments afterwards, because, as it just mentioned, the diagnostics are very sparse. And once you have been able to validate the simulations against the experiments, then you have a wealth of information available in the simulations that is just essentially impossible to gain through the ability to have diagnostics that can measure things. And a key thing here is that this field has not typically had widespread use of simulations for these purposes. It's, in fact, rather rare due to the lack of open codes. But this really needs to become the norm, because if that can be the case, then experiments will be better able to address the scientific questions that are being asked. There'll be the ability to utilize these facilities better. There'll be the ability to do peer review so that there will be a competition, on open and level ground about what would be the best use of the access to these facilities, and also the best science can be extracted from these experiments after they're done. And 3 years or so ago, DOE and NSA Advanced Simulation Computing Office selected Flash to be such an open code, not necessarily the only one, but to be such an open code. And so we have had an HEDP initiative at the Flash Center for the past 3 years to use Flash as it was, a very professionally written and very well-tested code as the foundation for adding these high-energy density physics capabilities. And this slide just gives you a little flavor for some of the kinds of simulations that Flash has been well known for in the past. The code itself is multi-physics finite volume Eulerian code, and with a framework whose capabilities include adaptive mesh refinement, so you can put resolution where the action is, where you need it. It has multiple state-of-the-art hydrodynamic solvers, and then the notation of high-energy density physics. 1T means that you have a plasma where the electrons and the ions both have the same temperature, but in the new capabilities that have been added to the code, it's possible to treat situations which occur frequently when you have intense lasers striking material, where the electrons are very hot, the ions are colder, and also the radiation has a different temperature. So that's called the 3T regime. We also have a state-of-the-art MHD capability that has 1 and 3T, and we have implicit solvers in the code for diffusion using the Hyper library, and that's currently being used to model thermal conduction, radiation diffusion, and viscosity. Many physics modules relevant to astrophysics and cosmology exist in the code and have for a very long time, including gravity and nuclear burning. There's a generic, highly capable particle framework that's used for basic particle and cell simulations, laser ray tracing, and also back into the astrophysics cosmology arena, dark matter, and tracer particles for all kinds of different hydrodynamic flows. The code is in widespread use around the world. It has a very broad, in terms of scientific topics that it's being used for, and also in terms of geographical spread. It scales well to over 100,000 processors. We used it on the Intrepid IBM BGP with over 100 million CPU hours typically. This year we're actually an early science user on the IBM BGQ, the Mira, with 150 million of early science hours plus another 100 or so million in the Insight program. So we're a very, very voracious consumer of cycles for these simulations. Flash is extremely portable. It can run on your laptop all the way up to these leadership class computing facilities of the Department of Energy. And it's composed of interoperable modules. So when you're doing an application, you only link and compile those capabilities that you need for the problem of interest. It's professionally managed software with daily automated regression testing on a variety of platforms and version control, coding standards, extensive documentation, including inline, a user guide, and a developer's manual. And we have also had extensive contributions, including quite major contributions from our user base, and we have a policy for that. Currently, nearly 1,200 scientists have used Flash, and over 800 papers have been published using Flash directly. So this is the simulation code that has now been made into a highly capable open code for the academic HEDP community. And we're engaged with the order of a dozen experimental groups, both in the US and the UK and in France in the use of the code. What I'm going to tell you about is one case study here of how the simulations have helped to create a possibility for transformational scientific discovery. And the topic I'm going to talk about is one of cosmic magnetic fields. As I mentioned in my first slide about high-energy density physics, many of the motivations for the phenomena and the key fundamental physical processes that are studied in HEDP come from astrophysics or cosmology, and this is one such. We know that the universe is permeated by magnetic fields that range from very, very small values in between galaxies and clusters to values of the order of a few microgauss in galaxies and in galaxy clusters. The issue is, where did that field come from, and how did it come to have the value it has today? So that's really two questions. One, what process or processes created the seed fields, and then what processes were able to take those seed fields and amplify them to the very much larger values that we often see around us in the universe today. And so that's the question that we're trying to address. Just to give you an idea of how we know that there are microgauss fields in galaxies and galaxy clusters, here's an example. This is a rich cluster of galaxies, and what we're seeing here is, in fact, the X-ray emission from this cluster of galaxies. And what turns out to be the case is that behind this cluster at various places, and even embedded in the cluster, are galaxies that are radio sources. And so when the radio emission comes from those galaxies to us through the cluster, it turns out that the magnetic fields in the cluster cause Faraday rotation of that radio emission. And by measuring that Faraday rotation, we can get this estimate of what the magnetic fields are in the galaxies. And so here are, just 4 examples of such radio galaxies that are used to probe the fields in these clusters. And typically, the fields are considerably larger near the core of the cluster, and then kind of smoothly die off as you go out to the edges of the cluster. So what could actually create fields in the universe from nothing? One of the most promising mechanisms is what is called in this field the Biermann battery mechanism. And really what's happening here is that when there are gradients in the electron density and in the electron pressure that are not aligned, then the result of that is the creation of magnetic fields from nothing. And in a microscopic way, what's really happening is that when you have asymmetric shocks, you're going to have gradients not only behind the shock in the pressure and the density, but you'll have gradients parallel to the shock face because the properties of the shock, it's asymmetric, are varying along the shock face. And so you'll have cross products of the density and the pressure gradients. And microscopically, really what's happening is when you have these large pressure gradients, the inertia for the electrons in the plasma is much less than it is for the protons. And so the electrons are accelerated relative to the protons, and there's a drift current of the electrons that results, and that's really the source of the electric field and therefore the magnetic field. So this is capable of producing seed fields, but many orders of magnitude smaller than the typical fields that are measured, for example, in galaxies and clusters. So we'll have to figure out what's going on with the present-day values of these fields. How do those come to be? But just as a cartoon here, the key thing here is that if you have shocks that are symmetric, for example, spherical in this case, or circular or planar, you won't have these cross products or these gradients, so you won't generate any magnetic fields from nothing. But if you have asymmetric shocks, like are shown over here, then you will get the creation of these fields. So we should examine the universe and see what we can say about whether such asymmetric shocks are very common. And what I'm going to show you is a beautiful simulation of the formation of a galaxy from smaller entities, from smaller halos of gas and dark matter that merge into a larger galaxy. And the 4 panels that are showing here is on the upper left shows how the metallicity changes with time. On the right-hand side here is going to be the density, so this is really the gas density. Over here is the temperature, and this is particularly useful for seeing where the shocks are. And then over here is the metals come from once there are dense enough regions, stars start to form, and then for supernovae of massive stars, they live a very short period of time. they create a lot of metals and then explode, spewing them back into the intergalactic or intergalactic material in this case. And so the result of that was there'll be production of metals that can be visible. So I will actually show this a couple times so that, and I would, give you just a chance to sort of see what's going on. So here you can see in the density what's happening. The universe is expanding, and you can see that gravitational attraction is causing filaments, and then these filaments to start falling into where this galaxy will form. And you can see over here in the temperature that there's a lot of things going on. You can see several big shock waves moving out from where the galaxy is forming here. But there's accretion of many, many smaller entities and even medium-sized entities into this galaxy. You can see this going on. And every one of these processes is involving very, very strong, very, very high Mach number asymmetric shocks. So it is thought, and I'll just run it one more time. I'll probably have to back up once to be able to rerun it. So this is why the Biermann battery mechanism is thought to be a very promising origin for the seed fields in the universe. It's bound to be happening here. There's no avoiding it. It's got to be happening. Other processes may be contributing, but this one we know has to be happening. So how could we try to look at this and learn about shock-generated magnetic fields and then how they might be amplified? Clearly, this is creating a turbulent environment. So you can think about the dynamo, where the typical dynamo situation, you have a magnetic field loop, for example, and you twist it, and then you fold it over. And that doubles the field value. And then you twist it and fold it over. In the kind of chaotic, turbulent circumstances in astrophysics, it's not going to be so simple a method. It'll be happening chaotically in all dimensions, but the same basic thing is happening. So turbulence can amplify by many, many orders of magnitude the fields that are seen. So we want to investigate these things in the laboratory. And up till now, it's really been impossible to do simulations that can actually simulate this kind of phenomena of shock-generated magnetic fields and their amplification by turbulence in the laboratory. And the reason is that such simulations require codes that are correctly and accurately able to treat this Biermann battery mechanism, and that turns out to be quite challenging at shocks. But in addition, in order to reach fluid Reynolds numbers in the thousands and magnetic Reynolds numbers in the many hundreds to thousands requires very, very high spatial resolution. The reason is because you need to not have numerical dissipation dominating what's happening. So you need to be able to get to situations where there's a large dynamic range between the driving scale of the turbulence and where the magnetic field is being dissipated. And if you have only a small range of length scales you resolve, you will not have enough dynamic range to allow the turbulent amplification to happen. You have to have a very large dynamic range, at least factors of 100 in the range, or even better yet would be something like 1,000. So to date, the platforms have not existed that can do simulations with this kind of spatial resolution in 3D. And there haven't been codes that have correctly treated this Biermann battery mechanism as well. So it hasn't been done up till now. On the experimental side, it's typically been trying to investigate these kinds of dynamo effects of amplification, in particular by laboratory experiments that use conducting fluids, for example, liquid sodium. But the problem is that the scale, the size scale of these apparatus are too small to give you the dynamic range that you need to have Reynolds numbers, and particularly magnetic Reynolds numbers, that are in the many hundreds to 1,000. So as a result, although there's been interesting results from these experiments, they have not really been able to get into this dynamo regime, let alone the turbulent dynamo regime, to give us any fundamental understanding of what's really going on. So at this moment and going forward, the computational power that we now have and the advent of high-power laser systems has opened up the possibility of really trying to understand these two fundamental processes, the creation of magnetic fields at asymmetric shocks and their amplification by turbulence. What are the drivers for the petascale computational resources? I've kind of mentioned one of them. That's the spatial scale. But there's really two other ones. First of all, in these kind of laser experiments, the laser is on typically for only a nanosecond. And that means that you have to actually resolve the hydrodynamics or the MHD that's happening because of that on something even a finer time scale like picoseconds. But when you're watching the shock go forward and you're trying to measure it, it's often at centimeters away, and that means you have to follow this for microseconds. So it's a huge number of time steps that have to be handled in the simulation. And also, the proper treatment requires a 3D simulation. We know that turbulence does not behave the right way it really does if you only model it in 2D. So these are fully 3D simulations that are required, and they also require this very high spatial resolution. So Gianluca Gregori and his high-energy density physics group at Oxford had an incredibly novel idea of how to tackle this experimentally. And what they did was they persuaded several of the laser facilities to take these vacuum chambers where they conduct these experiments and fill them with gas. And he had quite a time persuading this to be done. But once he was able to do this, by having a laser hit a target and exploding it, creating a blast wave, that blast wave, if its target's hit from one side, will not be symmetric, it will be asymmetric, and it's moving now into a gas and ionizes it, producing, making a plasma, and all the right conditions are present to see the Biermann battery mechanism happening right in the laboratory where it can be studied. And the first results he got from this were from the Lully experimental facility in Paris, and they were published in Nature in January of 2012. So what we hooked up with them then soon after that and have been using the flash code to help understand those experiments which were already done, but even more to help design the new experiments to try to meet these challenges of understanding not just the generation, but the amplification of these fields by turbulence. And so what we came up with at the Flash Center was the idea of putting a grid in the domain between the target and the three-axis little coils that measure the three components of the magnetic field. So these are two simulations that Petros Tseferakis, the lead person in the Flash Center, credible guy who's doing these kinds of simulations. And what I'll show you here on the left-hand side is without any grid in place. So there won't be any creation of turbulence here. Over here you can see the rigid bodies that we're able to put in the flow. And the top, you'll see the density, and you'll see that the hydrodynamics of what's happening when this laser hits the target is very complicated. And in the bottom half, you'll see the magnetic field that's generated. So I'll run these movies separately so you can first see without the grid. And I'm going to try to stop it after it just starts so that you can get a feeling for, the target is actually right there. You can just see, because in the density, you can see something there. You can also see it over here. The magnetic field, there isn't any, so you don't see anything there. So I'll try to start it and stop it really quick. So this went a little far, but what you can see here is that this is the direction that the laser came in. It hit the target here, and already very complicated hydrodynamics is happening. And I'll just keep it going. And there's a magnetic field that's being created, and you can see it's very strong near the shock and right behind it by these steep gradients in the electron density and the pressure. Okay? It continues to go out, and I'm letting it run here, even though not much is happening, to just give you an appreciation of how challenging these simulations are when you have to resolve picoseconds and then keep going out to microseconds. So now we put a grid in, and what you'll see is, and these simulations are 2D cylindrical, So they will show some turbulence, but not the full three-dimensional turbulence. They also will show compression of the magnetic field as the flow squirts through the grid. And so two things that happen here are, one is that the shock goes out faster and further when there's a grid there, surprisingly enough, but also there's turbulence. And again, the target is about right there, and then over here at about 2 centimeters is where the three-axis probes will sit. So these simulations are really key to seeing how strong the field would be, how energetic the laser should be, what the size of the target should be, and even more important kinds of things like what should be the grid opening size in the grid that would maximize the amplification of the magnetic fields, how close should it be to the target, where should it be the three-axis probes, and so on. So the kind of experimental design here was really crucial. And these simulations were featured in the proposal to the Vulcan facility in the UK, and it was successfully. It was our time, and experimental time was awarded. And here's the setup that was eventually that we adopted. It's very similar to the simulations you can see. Here's a spherical target. This one was it was plastic. Here's the laser beam coming in from this side. Here's the grid here. 1 millimeter opening sizes turned out to be best. And then from the simulations and for other theoretical reasons that we were able to confirm or to support that the three-axis coil measurement should be 10 times the distance of the opening of the grid. So the grid is 1 millimeter, so the probe should be 1 centimeter away. And so what happened when we did the shots? Gianluca and his team ran 200 shots. So one of the things here is these things are over in an incredibly short time, but on facilities like Vulcan, you can do them over and over again. So you get to be able to measure things at different times with different parameters, but also you can check on the shot-to-shot variation. On the left here is the situation, and here's the laser coming in from this direction. You can see the asymmetric shock here. In this case, it was a carbon rod. There's no grid here. This is the probe, which at the very tip has 3 little coils, the 3 axes that are measuring the magnetic field in these 3 directions. And on the right-hand side is exactly the same thing, except the grid is in place, and you can see that beyond it, there was a lot of turbulence in the flow. So the next slide here compares the simulations with the results of the experiments. And so what's shown here on the bottom is without the grid. And you can see here's the shock front. It's just reached the position or passed it a little bit, the place of the coils. And so what we did is we took, the coils would be right there on axis. We took a cross-sectional cylindrical volume, the size of the coil that would be right there to average the field over that. And what we saw is the field that looks like something like this. So it was quite a long time. I mean, relatively speaking, it was a longer time before the field started appearing, and the peak was when the shock crossed the position of the coils, and then it decayed afterwards. And when you look at with the turbulence, what you see is 2 things. One is the shock reaches the position of the coil sooner. It's the squirting through the apertures that's in the simulations. It's shown, and it's amplified by factors of 3 or so over without it. And you go over here and look at the experiments, and you see 2 things. One is, indeed, without it, here's the field component we're most interested in here. With it, it's much stronger, again, factors of several, and it peaks earlier. The shock is arriving earlier. So all semi-quantitative agreement here with the simulations and the experiment. So if we go now to think about, okay, we've really shown some minimal, only factors of a few, amplification of the fields by turbulence. But we really want to look at something much stronger. How can we do this? Well, these are simulations that were done of the velocity of the magnetic field, the velocity structure in the flow here on the left and the magnetic field on the right. And the upper panels are ones for the situation described in detail over here, where the dissipation physical scale of the magnetic field is much smaller. There's a big dynamic range from the driving scale to the dissipation scale, but it's much smaller than the dissipation scale for turbulence in the fluid. So there can be no things in the fluid that aren't in the magnetic field structure. And that's exactly what you see here. On the top panels, the magnetic field looks very exactly similar to the fluid. In the case where the Prandtl number is small, then in fact the magnetic dissipation scale is much larger scale than the fluid. And so you can see much finer structure in the turbulence here than is reflected in the magnetic field. So what you want to do in the simulations particularly, but in the experiment as well, is this is the regime that we're in. You want to make sure you have the dynamic range to allow this kind of magnetic turbulence to exist. And you are wasting resolution and computational resources if you go down far below this dissipation scale, because it ain't going to do nothing. So here's the results of the Vulcan experiment, where the energies of the laser were not so great, but still very interesting. So what we see here is the following. I'll explain on the left-hand side here the situation. If you have a low magnetic Reynolds number, so a lot of immediate dissipation of the magnetic field, then there is this power law, the Golitsyn spectrum, which is to the minus 11/3. And so with that, what that means, the Reynolds number is low, and you actually can measure where it flattens out here what that magnetic Reynolds number is. But as you go to higher magnetic Reynolds numbers, what you see is this power law, which is the power law spectrum of the magnetic field as a function of length scale, it becomes flatter and flatter and flatter. And anything that's flatter than this represents the start of nonlinear amplification of the field by turbulence, which is the holy grail in both simulations and experiments in this whole field. If the power law becomes flatter than -1, you're actually fully in the nonlinear regime. So this gives us a signature to know exactly what's happening. So let's ask ourselves, what happened in the Vulcan experiment? And here's the power law, or at least the behavior without the grid. But with the grid, we see a complete match to this -11/3 spectrum. So we are getting amplification of the field by factors of several, but it's completely in the linear regime. We do not see a flatter than -11/3 spectrum. And we can also measure the Reynolds number here, and it's only a few. But what we did is we changed the parameters of the experiment. And so here's what it looks like in experiments where we were able to generate stronger turbulence. And what you see here, the earlier experiment fell on this kind of line of -11/3. But these are falling on -9 and -8. So they're showing that we are beginning to get nonlinear amplification, even in these really small laser facilities, relatively speaking, like Lully in Paris and the Vulcan at the Rutherford Laboratory in the UK. So what lies in the future? We have an experiment that will be happening hopefully later this year at the Omega Laser at the University of Rochester. And I was just on a phone call this morning about this. And we expect to reach Reynolds numbers there in the lower few thousands, magnetic Reynolds numbers. That should enable us to get into the nonlinear regime, because if I go back and show you here, and you look at what these values on the right here is, when you get above a few hundred in the magnetic Reynolds numbers, you're getting slopes that are fully in the nonlinear regime. But the real exciting thing is Gianluca and his team have an approved experiment on NIF. And in NIF, we should be able to get to magnetic Reynolds numbers of the order of 10,000 or so. So this will be a spectacular ability in the laboratory and with our simulations with the power of 10 petaflop and 100 petaflop platforms over the next few years to be able to, both in simulations and in experiment, to probe these fundamental processes of how the magnetic fields in the universe are created and once seed fields are created, how they're amplified to the much, much larger values that we see around us. And I'll just close with that and leave my summary. Thank you very much.